6, and this is, we call it L'Hôpital's rule. Some people call it L'Hospital's rule, but it's really, I like to call it L'Hop. But anyway, L'Hôpital was a French mathematician who was actually taught by some very famous, the Bernoulli family, I think was his, who were his tutors. And Bernoulli is credited for writing the first, or one of the whole Bernoulli family is a Basel, Swiss family that is famous, has famous mathematicians even to this day in the family. And L'Hôpital was a French nobleman, and so the French, this is what they used to do for fun, the really rich French guys, instead of like what Paris Hilton does for fun, what they would do is they would learn math for fun. It was like, it was something cool to do. Like if you were so rich that you could waste your time learning math, you really had some money. And so he studied under Bernoulli, who wrote the first calculus book, but L'Hôpital had the money to fund the book. So he published the book under his name and kind of took credit for a lot of these theorems that perhaps were not his theorems, but since he had the money to publish the book, he sort of got the credit. So it's L'Hôpital's theorem, but I wonder whether it's really L'Hôpital's theorem or another one of Bernoulli's. But I'm sure there was some sort of an agreement reached between the writers. So here we are. And what you look at, you remember this? What do we call that? What do we call that in here? Nobody? This was yucky. Don't you remember? Okay, and we had to be clever, like we used some algebra techniques, or we used the sandwich theorem, or we used some different theorems to try and solve those limits. Now, the derivative is based on a limit. It should make some sense that we can use the derivative to help us compute some limits of indeterminate forms. So today, it seems kind of weird. We're going back to another idea. We're not doing maximization or really anything, but we're looking at another application of derivatives, which is to help us solve limits. And you're going to love this application because you finally get to do what you've always wanted to do, which is when you see a quotient, take the derivative of the top and take the derivative of the bottom, instead of using the quotient rule. Now, you have to recognize that what you're doing is you're looking at the limit of a quotient and you're applying what's called L'Hôpital's rule, but it feels very intuitive to do that, so it feels pretty good. Okay, so we are going to use the derivative to help us compute some limits of indeterminate form, and it leads us to L'Hôpital's rule. He was a French nobleman who wrote the first introductory differential calculus text in the late 1600s, and he had some very famous tutors, including John Bernoulli, who actually discovered this rule. You can read more about both these men, as well as the proof of the rule, in section 4.6 of your text, your book. I will state it here without proof and work some examples. So, this is the strong form of L'Hôpital's rule. Say you have two functions that are equal to 0, and that they're differentiable on an open interval I containing A, and that the derivative of the function is not 0 as long as if x is not equal to A. So it's only at A that they're equal to 0 and the derivative is true. Well, then it turns out that the limit of f of x over g of x as x approaches A is equal to the limit of the derivative of each of the functions, assuming that the limit on the right side exists. So if this limit exists, then you're able to do this. And this makes it really fun, because remember limits, we like to plug it in. So what this is saying is if you plug it in and you get 0 over 0, that's called an indeterminate form. And you can use L'Hôpital's rule to take the derivative of the numerator and the derivative of the denominator and then try plugging in again. And it might work out that you now are able to get an answer. Does that make sense? And it turns out that if you got 0 over 0, you could do a derivative again. So you can do it as many times as you need to until you get down to an answer. So you can imagine, like if you have a polynomial over a polynomial, eventually they differentiate down to just constants. And so when you plug in, you're going to be good. So let's look at some examples. Here's what. Try direct plug-in to see if you get the indeterminate form. These are your two indeterminate forms that if you don't get this, it doesn't make sense to use L'Hôpital's rule. But you can continue to differentiate f and g separately, so as long as you get the indeterminate form, or you finally get a limit to work. Okay. So on problems 1 and 2, we're going to evaluate both ways. We're going to use L'Hopital's rule, and then we're also going to look at the methods from Chapter 2. Okay? So the first thing you want to do is plug in to verify that you get the yucky. All right, so when we plug in, we get the limit as x approaches 2. This is 2 minus 2 over 2 squared minus 4. Yes, 0 over 0. So that's yucky, which is good. All right? Because yucky means we can use L'Hopital's rule. The indeterminate form is the better language. Okay, according to L'Hopital's rule, the limit of this function as x approaches 2 is going to be equal to the limit of the derivatives of the functions. So the derivative of x minus 2 is just 1. And the derivative of x squared minus 4 is 2x. You got with me? So I take the derivative of the top, derivative of the bottom, and now I can plug in. And what do I get? Well, I get 1 over 2 times 2, or 1/4. Okay? So that's using L'Hopital's rule. And I always say use L'Hop. Okay, now let's try it the old way. Old method from Chapter 2. Does anybody remember? What was the method that we used in Chapter 2 to handle this problem? Come on. It's screaming to someone. What is it? What do we do in Chapter 2? What do you want to do with x squared minus 4? Like if you were hanging out with x squared minus 4, what would you want to do to it? Factor. Yeah, me too. I would want to factor it. So I would write this as x plus 2 times x minus 2. Are y'all with me? And then what happens? Cancel. The x minus 2's cancel. So you have the limit as x approaches 2 of 1 over x plus 2, right? Now we do a plug-in, and we get 1 over 2 plus 2, also known as 1/4. So notice, you get the same answer whether you use the methods from Chapter 2 or L'Hopital's rule. You get the same answer. Okay? Now, this one was easy to do with the methods from Chapter 2. It was easy to factor. That's not always the case. So, we'll look at some where they're more complicated, and it's funner or more fun to use L'Hopital. Okay. For example, this problem is more fun with L'Hopital. All right, so let's try, what do we need to do first? Well, before you can apply L'Hopital's rule, you need to plug in and make sure that it is in an indeterminate form. You have to have either 0 over 0 or infinity over infinity to use L'Hopital's rule. Okay, so when we plug in, we're going to have 1 minus the cosine of 0 over 0 squared. The cosine of 0 is 1, so this is 0 over 0, right? So this is yucky. So we can use L'Hop or L'Hopital, okay? So L'Hopital's rule tells us that the limit of this function is going to be the same as the limit of the derivative over the derivative. So what is the derivative of 1 minus cosine x?
Sine x.
It's going to be positive sine x, yes. Over 2x, right? Now, can we plug in, what happens when we plug in? Well, we're going to get the sine of 0 over 2 times 0. The sine of 0 is still 0, and then that's 0. So we're still yucky, right? But according to L'Hopital's rule, we can use it, we can do it again. So what is the derivative of the sine of x? Cosine x over the derivative of 2x, which is 2. Now we can plug this in and plug in, and we'll get the cosine of 0 over 2, which is 1/2. Okay? And so that is our solution. All right. Now, that was easy, wasn't it? Now, if you wanted to do this actually with the techniques from the last chapter, I'm not going to do it because I don't really want to. But if we wanted to, what you have to do is multiply by the conjugate of 1 plus cosine x on top and bottom, and then you would get 1 minus cosine squared x, which you could write as sine squared x. And then you know that sine squared x over x, that limit is 1, and you would get there. I mean, you get there eventually, but you have to do some algebra, okay? So do you see how much more fun L'Hopital's rule was than remembering about conjugates and the Pythagorean identity and then all of that, okay? Good. So let's do some more of these, okay? What's the first thing you have to do? Plug it in. All right. So we'll do negative 3 cubed minus 4 times negative 3 plus 15 over negative 3 squared minus negative 3 minus 12. Negative 3 cubed is negative 27, and then this will be plus 12 plus 15, so that's good, over 9 plus 3 minus 12. So yes, 0 over 0, correct? So that is yucky, and we can use L'Hopital. Okay? And so, Robinson, what will I get when I use L'Hopital?
Squared minus 4.
3t squared minus 4
Good.
over 2t minus 1.
2t minus 1. So doesn't it feel good? You know that's illegal. If you're just taking a derivative and you have a quotient, you have to use the quotient rule. But L'Hopital's rule lets you take the derivative of the top and the derivative of the bottom, which is what you always wanted to do. So, right? Just notice that you're doing limits. You're not doing derivatives. You're just doing a limit. So it is a different thing. It's fun because we've always wanted to do that. Okay, now we'll plug in. And we'll do 3 times negative 3 squared minus 4 over 2 times negative 3 minus 1. And so that's 27 minus 4 over negative 6 minus 1. So that is 23 over negative 7, right? Or negative 23 over 7. We like to put the negative in the numerator. Everybody like that? Yeah. Okay, let's try number 4. First, you have to verify that you can use L'Hopital. So let's plug the 0 in. We do 0 times 1 minus the cosine of 0 over 0 minus the sine of 0. That is going to be 0 over 0, so this is yucky. So we're going to use L'Hopital. Now we have to be careful in the numerator because we will have to use the product rule when we take the derivative in the numerator. So can we do this? Can I just kind of talk you through it instead of writing out the u and the v? Are y'all about there? Yeah? Okay. So the derivative of u is 1 times the v, which is 1 minus cosine x, plus the derivative of 1 minus cosine x, which is sine x, times the u, which is x. Okay? And then the derivative of this is just going to be 1 minus cosine x. Now, when we plug in 0, what happens is we will get, if we put 0 in here, what's 1 minus 1, which is 0, and then this is 0, and then here's 1 minus 1, so we get 0 over 0, which is yucky. So we're going to use L'Hopital. Okay, so let's try L'Hopital's rule again. The derivative of 1 is 0. The derivative of minus cosine x is going to be positive sine x. And then plus, we have a u and a v here. The derivative of sine x is cosine x times the v plus the derivative of v, which is 1, times the u, which is sine x, all over the derivative here, which is going to be, that's just going to be sine x. Okay, now what happens is we get 0 here, 0 here, 0 here, and 0 here. So again, 0 over 0, which is yucky. Okay, so let's try to use LaHop again. Isn't that exciting? I know. Okay, so what's the derivative of the sine? The derivative sign is actually positive. Cosine plus, all right, the derivative of cosine is negative sine times x plus the derivative of that, which is 1, times this, plus the derivative of the sine, which again is cosine. I guess I could have put 2. I could have grouped those, but I didn't. Sorry. All over the derivative of sine, which is cosine. Now this is good because finally we just have a cosine in the bottom, and the derivative, I mean, when you plug in 0, you get 1. So we're no longer going to get 0 over 0. Let's see what we get in the numerator. If I plug in 0, the cosine of 0 is 1. This will be 0. This will be 1, and this will be 1. And then the cosine of 0 is 1. So I get 3. That's my answer. That was fun. Okay. We haven't thought about the derivative of 2 to the x in a while, have we? Have we done it? Do you guys remember it?
I just know that you got over keep stuff inside and then derivative. So
It's the derivative. If you can look at this on your sheet, that good derivatives and integral sheet, that's one I recommend you have around. The derivative with respect to x of some base, so some number to where the variable's in the exponent, so a to the u, is, remember derivative of e to the x was just e to the x? Well, if it's not base e, if it's base 5 or whatever, it's a to the u, so 5 to the u, and then you have to do ln a. So this is going to be a to the u, and then you have the ln of a. And then you, of course, have du dx. Okay, so the derivative with respect to x of 2 to the x is going to be just 2 to the x ln 2, and the derivative of the u here is just 1. But if it had been 2 to the x squared, then that would have been more exciting, maybe. Okay? All right. So, is this L'Hopital rule worthy? Well, yes, because you do get 0 over 0 when you do a direct plug-in. So we're going to use L'Hopital's rule. Okay, now we're going to have a product rule in the numerator. So the derivative of x is 1 times 2 to the x plus the derivative of 2 to the x, which we just figured out was 2 to the x ln 2 times the first, which is x. And that's all over 2 to the x minus 1. Now, oops, just kidding. We have to take the derivative of the denominator, which will be 2 to the x ln 2. Okay, I like that better. Okay, now when we plug in, we're going to have 2 to the 0 plus 2 to the 0 ln 2 times 0 all over 2 to the 0 ln 2. Well, 2 to the 0 is 1. This is ln 2 times 0, so that's just 0, over 2 to the 0, which is 1, so this is ln 2. So the answer is just 1 over ln 2. Okay? So it's kind of fun because you're getting to think of some derivatives maybe you haven't thought about in a while. It's good to always have them, hanging out. Like the derivative of ln x. Do you guys remember the derivative of ln x?
U prime over u.
Yeah, the derivative of ln u is u prime over u. So here it's going to be 2x plus 2 over x squared plus 2x. All right, so but before we do the derivative, we have to make sure that this in fact works. So you need to do the plug-in. this is going to be the ln of 0 squared plus 2 times 0 over the ln of 0. Now, you may know that you can't take the natural log of 0, right? Do you guys remember that? It's not defined in the domain. E to no power will ever be 0. But what you may remember is that the natural logarithm function looks like this, and it actually has an asymptote. As you approach 0 from the right, you have you're going to infinity, negative infinity. Okay, so the ln of 0, this is really negative infinity over negative infinity, or infinity over infinity, which is what we call an indeterminate form, and so it allows us to use L'Hopital. If you get 0 over 0 or infinity over infinity, you can use L'Hopital's rule. So we're going to use L'Hop, or L'Hop. And so we will take the derivative of the numerator and then the derivative of the denominator. So the limit as x goes to 0 from the right of ln x squared plus 2x, this is going to be 1 over x squared plus 2x times the derivative of the numerator, which is 2x plus 2, over the derivative of ln x, which is 1 over x. All right, now, before you plug in, you want to clean it up a little bit. So this is 2x plus 2 over x squared plus 2x, and then you're going to multiply that by x over 1, because dividing by the fraction is the same as multiplying by the reciprocal. Okay, and then you can clean this up some more. You have 2x plus 2. If you factor an x out of the denominator, notice that you can cancel those x's, which is a good thing, because now when we plug in 0, we get 2 over 2, which is equal to 1. So it's really fascinating that you can have quite challenging functions like ln x squared plus 2x over ln x. I mean, those are not trivial functions. But now you have enough skills to evaluate what the limit is as x goes to 0 without having to look at the graph. You know, just using the knowledge that you've gained in this classroom, just in this classroom. Isn't that awesome? I mean, it's so useful, like in life. I don't know when, but anyway. If you wanted to impress your friends or something. Some math is we just do because we can. That's what I tell students. It's a little exercise, a little brain exercise. Okay, let's see if we get infinity over infinity on this one. E to the infinity plus infinity squared is probably pretty big. Over e to the infinity minus infinity, you can rack your brain on that a little while, but I'll tell you that this is, in fact, infinity over infinity, which is indeterminate. And so we can use L'Hop. Okay, so the limit as t goes to infinity of e to the t is just what? The derivative of e to the t is e to the t plus the derivative of t squared, which is 2t, over the derivative here is e to the t. The derivative of that is just 1. Okay, now, if you plug infinity in here, you're going to get infinity over infinity, so you're going to want to use L'Hop again. And so the limit as t goes to infinity, this will be e to the t plus, this is 2 over just e to the t. All right? Now, this is, again, infinity over infinity, so we'll use L'Hop one more time, and we'll get the limit as t goes to infinity of e to the t over e to the t. Well, hello, that's just 1, right? And those reduce, and so you get the answer there is 1. I don't want to be facetious about what I said about how this is kind of seems sort of esoteric. What happens in calculus is I am sort of trying to fill your toolkit. So when you go to other classes and you're faced with a limit, which you can be faced with a limit in other more advanced courses, remember L'Hopital's rule. Okay, and this is today, and then you'll have it on the test, and you'll have it on the final. But let it be your friend. It does get lost in the toolkit. Sometimes we forget, like we see limit and we freak out. But a lot of times L'Hopital's rule just will get us the answer really quickly. Okay, so it turns out that you can have other indeterminate forms. I mean, like if you're trying to go to sleep at night and you just want to freak yourself out, like it's scary, you want to be scared, just spend some time thinking about 1 to the infinity. Is it always 1? 0 to the 0. What is it? What does it mean? Infinity minus infinity, is that 0? Infinity times 0, is that going to be 0? Do you see what I'm saying? Infinity to the 0 power, what does that mean? You do not know. You do not know, and we're going to talk a little bit about them right now, but these are weird indeterminate forms. So you can't always say that 1 to the infinity is 1, although that feels good. And you cannot always say that 0 to the 0 is 1, I guess is what you might want to call it. Because anything else to the 0 power we want to call 1, right? Especially when we're thinking about functions. So this leads us to some really awesome results. My personal favorite result of all time is coming up. Okay, so it looks like I don't know what my notation was doing there. Okay, so it's if the limit as x approaches a of ln of f of x equals L, then the limit as x approaches a of f of x is equal to the limit as x approaches a of e to the ln f of x, which is equal to e to the L. Okay, so what they're telling you here is if you have a function that's just like infinity to the 0 power or 0 to the 0 or 1 to the infinity, some weird function, it may be better for you to first take the logarithm of that function, consider that limit, and then e it. Have you heard me e it before? You know, e the limit. Whatever you get for your limit of the logarithm, it'll just be e to that will be the limit of the original function. Okay? So that's another little technique that's fun about logarithms. So let's see if I can explain that a little better on this problem. Now, on this problem, if you do a direct plug-in, you get 1 to the 1 over 1 minus 1, which is 1 over 0. Well, and these are limits. This is as x approaches 1. So as x approaches 1, this is going to go, where is this going to go? If your denominator is getting smaller and smaller, where does this whole thing go? It goes, yes, it's going to infinity, like 1 over 1/10, 1 over 1,000, 1 over 100, 1 million, you getting it? So this is going to infinity. So this is like 1 to the infinity, which is an indeterminate form. So what we will do is consider, so if we go back to that theorem, if we let this x to the 1 over 1 minus x be our f of x, according to the theorem, we can then think of the ln of f of x. So the ln of f of x will be equal to the ln. Remember, the cool thing about the ln function is that it pulls out, it's the power rule. We can invoke the power rule. So it'll be the ln of this thing. But the power rule brings this in front. And so this is going to be the ln of f of x is equal to 1 over 1 minus x times the ln of x. Now, this will be 0 over 0 if we look at the limit as x approaches 1. So this will allow us to use L'Hopital's rule. So if we consider the limit as x approaches 1 from the right of the ln of f of x, that will be the limit as x approaches 1 from the right of 1 over 1 minus x times the natural log of x, the ln of x, which is, when you plug 1 in, 0 over 0, or yucky. So we can use L'Hopital's rule, and the limit as x approaches 1 from the right, we can do the derivative of ln x, which is 1 over x, over the derivative of this, which is -1, And so this is just negative 1 over x, which is then just negative 1, right? When you do the plug-in. Okay, so we have the limit of the natural log. So to get back to the limit of the original function, what do we have to do? We have to e it. And so the original limit of f of x will be e to the negative 1, or 1 over e. Just take a minute and think about what just happened. All right, I did x to the infinity, or really where x was 1. And so I was looking at this 1 to the infinity. I mean, last time I thought about 1 to the infinity, I really thought that it would be 1. I mean, don't you think? 1 to the infinity seems like it'd be 1. And 1 to the million is 1. 1 to the 10 million is 1. But in this form, when it looks like 1 to the infinity, the answer is 1 over e. Really far from 1. It's like 0.2 something. Is that weird? Creepy? Cool? I don't know. All right, let's try this one. Number 9. What should we consider on number 9? Because if we put infinity in here, we're going to get infinity to the 0. Do y'all see that? You'll get infinity to the 1 over infinity, which will be like infinity to the 0. So we should take the natural log of this function and consider its limit. So let's look at the limit as x goes to infinity. If we take the natural log...
Miss Brooks, we have to go.
Okay, see you later.
See ya.
1 over 2 ln x. We're going to miss, hey, you guys watch the very end of this, because my very favorite function in the whole world comes up. It's really big time. So just scroll to the end if you can't get through the whole video. This is 1 over 2 ln x, and then ln 1 plus 2x. All right, so I just took the natural log, and then I invoked the power rule. Okay, and then now this gives me infinity over infinity, which allows me to use L'Hopital's rule. Okay, so the derivative of the ln of 1 plus 2x is going to be 1 over 1 plus 2x times the derivative of 1 plus 2x, which is 2, over the derivative of 2 ln x is going to be 2 times, or 2 over x, or 2 times 1 over x. Okay, this is the limit as x goes to infinity. And so I can write this as 2 over 1 plus 2x times x over 2. The 2's cancel, and I get x over 1 plus 2x. Sorry. Something up. And if I put infinity in there, I get what? Infinity over infinity, which means I can use L'Hopital again, and I will get the limit as x goes to infinity. The derivative of x is 1. The derivative of 1 plus 2x is just 2. And so that is my answer, 1/2. But it's not quite my answer. That's my answer for the limit of the natural log of the function. To get back to the original function, I have to e it. Okay? So the limit as x goes to infinity of 1 plus 2x to the 1 over 2 ln x is going to be e to the 1/2. So it's just crazy, huh? We looked at infinity to the 0 power, which feels like it should be 1, because anything else to the 0 power is 1. But for this function, we found it to be e to the 1/2. So, just interesting. I can tell you're thrilled. Okay. This is kind of a short lesson, because we're just doing the last problem now, which is my personal favorite. I like it so much that I typed it wrong. But if you printed it out, it should be x to the infinity. So let me just rewrite it, because I can't believe I did that. Of course, I'm too lazy, I guess, to redo this whole. You know, do you guys ever do this? Like you write something and it gets like, who knows where it is? Like it's like 3 computers ago, and so I would have to redo the whole, I have it in PDF form, but if I want it in Word form to go back and fix this, it would be a real hassle. And it shouldn't be, you say, well, it shouldn't be that big of a deal to convert from PDF to Word. But actually, when you're using equation editor, these equations like this, it's a real challenge. It's not if you just have regular English, but these equations. So that's my excuse. I should probably retype this lesson, though. Okay, because this is, if anybody knows this, I mean, if you know me, you know that this is my personal favorite function. And what does anybody know what this is? It just creeps me out. Like, it's perfect for Halloween. Because if you're at 1 plus 1 over x to the x, I just look at it, I'm like, 1 over x is pretty much 0 as x goes to infinity, right? I mean, like 1 over 1,000, 1 over 10,000, 1 over 1,000,000. And so I'm doing 1 plus nothing to the infinity. So it feels really good to me that this is 1. 1 to the infinity should be 1, right? But if you know the story, you know that this is not 1, and that just creeps me out. So here is the proof. If you had me for college algebra, or maybe even in this class, we looked at it before with our graphing calculator. Because what you can do is you can go to your calculator, and limits are no longer nearly as interesting as they used to be, because you can just type in numbers, whatever it is, and approach it. So like we could do 1 plus 1 over x to the x. Maybe if you do it right. Divided by x. And raise it to the x. And then you just go to your table and you just type in really big numbers, like 100, and then 1,000, and then 10,000. And what number are we approaching? 100,000. Who is that? Who's 2.7181? Yeah, that's E, right? It's not 1, and it's weird. E is that beautiful number that appears almost as often in the world as 1 or 0. I mean, it's just as beautiful a number as 1 and 0 and pi and I. I mean, these creepy, weird numbers that come up. And E does that. So we know, we have a sense that this is probably E, thanks to TI-84. But let's prove it. Everybody agrees that when you do a direct plug-in, you get 1 to the infinity, which is an indeterminate form. So let's take the ln. So if we do the ln, so if we consider the natural log of this function, the limit as x goes to infinity, this will be x ln 1 plus 1 over x. Now we get infinity times the ln of 1, which is 0. So now we get infinity times 0, which we wish were 0, but it's not. We're not going to fall for any of that stuff anymore. Whenever infinity is involved, you can just throw out all your basic rules that you used to know. Okay, and now this is another indeterminate form. 1 to the infinity is an indeterminate. Infinity times 0 is indeterminate. L'Hopital requires that it be either in the form 0 over 0 or infinity over infinity. So you have to be clever on this one, and I'm showing you this one to be clever, but in general, they may not be this challenging, but you have to be clever and rewrite this expression as, watch me, I'm so clever. The limit, I stole it from the book. The limit as x goes to infinity of, all right, well, I'm just going to write this as the ln of 1 plus 1 over x. But instead of x times that, I'm going to write it divided by 1 over x. It's legal, right? I unflipped and multiplied. I undid that. That's legal. And what happens now is when I do a direct plug-in, I get the ln of 1, because this basically goes to 0. So this is going to be the ln of 1, which is 0, over 1 over infinity, which is 0. As x goes to infinity, 1 over x goes to 0. Okay? So I forced it into an indeterminate form that I can now use L'Hopital on. Okay, so if I'm going to use L'Hopital now, I will need to take the derivative, and I have to think a little bit about this derivative. It's a little bit more challenging. All right, the derivative of the ln of 1 plus 1 over x will be 1 over 1 plus 1 over x times, all right, the derivative of 1 is 0. The derivative of 1 over x is, it's x to the negative 1, so it's negative 1 x to the negative 2. Everybody with me? Over, and then here I'm going to have negative 1 x to the negative 2. And the beauty there is what? Yes, these cancel. And so we get the limit as x goes to infinity of 1 over 1 plus 1 over x. And what is that limit when you do a direct plug-in? Yeah, it's just 1. Because this 1 over x goes to 0, right? Okay, but I was considering the ln of my function. So to get back to my original function, I have to do what? I have to e it. And so I get e to the 1. I e it. So I get e to the 1. So the limit as x goes to infinity of the original function, which is 1 plus 1 over x to the x, is e to the 1, or e, which is cool. I mean, trying to define e is tricky. This is one of the definitions of e. There's also a series definition of e, which is the sum of the series as n goes from 1 to infinity of 1 over n factorial. You'll learn about that in Cal 2. And what that means, I don't know if you've even learned the factorial. Have you all learned the factorial symbol, or you ever seen it before in statistics class maybe? Factorial means, like 5 factorial means 5 times 4 times 3 times 2 times 1. It just means take whatever n is and multiply by all the integers down to 1. You know, so like 3 factorial is 6. 3 times 2 times 1. 5 factorial is like 120. It's 5 times 4 times 3 times 2 times 1. So 20 times 6. Okay, and actually it turns out this is the series, and the sum of the series, this means 1 over 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial forever. That actually is e. It's another way to write e. So you'll learn about that in Cal 2. It's kind of exciting. Okay, so enjoy your